A telescope looked back 13.4 billion years and found galaxies that shouldn't be there, fully formed, massive, glowing. Scientists had a model for how the universe was built, and these galaxies broke it. We're going to travel through the oldest light ever captured, meet black holes that grew too fast, stars that never should have existed, and discoveries that are forcing physicists to rewrite the rulebook from scratch. If you enjoy what we uncover, like this video and subscribe. The universe just got a lot stranger. Let's go. Christmas morning, 2021. A rocket lifted off from a jungle launch site in South America, carrying the most expensive science instrument ever built by human hands. The James Webb Space Telescope. $1.1 billion didn't get this thing off the ground. $10 billion did, and it took 30 years to build. Engineers at NASA and their partners in Europe and Canada designed it with one obsession: see farther back in time than any telescope in history. Webb's golden mirror is 21 feet across, big enough to park 3 school buses side by side. It's covered in a thin layer of gold because gold reflects infrared light better than anything else we know, and infrared light is exactly what Webb was designed to chase. Here's why that matters. When light travels across billions of light years of space, something happens to it. The universe stretches it. What starts as visible light gets pulled into the infrared range, a kind of light the human eye can't see. Webb sees it perfectly. That means Webb can look at a galaxy 13 billion light years away and actually detect the glow of its stars. To get a clear view, the telescope had to escape Earth's warmth completely. Heat ruins infrared detection. So engineers folded Webb up like an origami crane, launched it, and let it unfold in space over the course of 2 weeks. Every step of that unfold had to work. If one of the 344 individual mechanisms failed, the mission ended. All of them worked. Webb parked itself at a point in space called Lagrange 2, about 1 million miles from Earth. That's 4 times farther away than the Moon. A sun shield the size of a tennis court keeps it cool, blocking light from the sun, Earth, and Moon all at once. On one side of that shield, the temperature hits 230 degrees Fahrenheit. On the other side, where Webb's mirror sits, it drops to negative 404 degrees Fahrenheit. That gap makes the telescope work. But here's what nobody outside the science world fully understood at launch. Webb wasn't just built to take pretty pictures. It was built to answer a specific question. After the Big Bang, the universe was dark for hundreds of millions of years. No stars, no light. Scientists called it the cosmic dark ages. Webb was built to look into that darkness and find the very first light that ever switched on. The team knew what they expected to find. Small, young, dim galaxies just starting to form, scattered and chaotic. The early universe should look rough, incomplete, like a city still under construction with only a handful of buildings finished. They aimed Webb at a tiny patch of sky and waited. What came back stopped the astronomy world cold. The galaxies in that patch were massive, bright, already fully built. Some of them looked more developed than galaxies that formed billions of years later. Scientists stared at the data and asked the same question, again and again. How is this possible? The answer they're still searching for is going to change everything we think we know about how the universe began. And it starts with understanding what light actually is when it travels across 13 billion years of space. Light is the fastest thing in the universe. Nothing moves faster. In 1 second, a beam of light travels 186,000 miles. That's fast enough to circle the entire Earth 7.5 times before you could blink. But the universe is so enormous that even light needs billions of years to cross it, and that creates something wild. When you look at something far away, you're seeing it as it was when the light left, not as it is now. The sun is 8 light minutes away. So the sunlight hitting your skin right now left the sun 8 minutes ago. You're seeing the past. Scale that up. The nearest large galaxy to ours is 2.5 million light years away. When you look at it, you see it as it was 2.5 million years ago, back when early humans were just learning to use stone tools on Earth. Webb looks at galaxies 13 billion light years away. That means the light hitting its mirror right now left those galaxies 13 billion years ago. Webb isn't looking far away. Webb is looking far back. Every image is a photograph of the past. But the universe doesn't make this easy. It's been expanding since the Big Bang, constantly stretching in every direction. When that ancient light set off on its 13 billion year journey, the universe was much smaller. As space stretched, the light waves got stretched along with it. Imagine drawing a wave on a rubber band, then pulling the band apart. The wave gets longer. That's exactly what happens to ancient light. Longer light waves mean lower energy. Visible light stretches into infrared. Ultraviolet light stretches into visible. The older the light, the more it stretches. Scientists measure this stretch and call it redshift. The higher the redshift number, the older the light. Webb is the first telescope powerful enough to detect galaxies with extremely high redshift. The previous champion, the Hubble Space Telescope, could see back about 13 billion years with effort. Webb can push beyond that, into territory no instrument has ever reached. When Webb's team released its first deep field image, a picture of a tiny sliver of sky, no bigger than a grain of sand held at arm's length, they counted thousands of galaxies inside it. Every single dot of light in that image was an entire galaxy. Some of them existed when the universe was less than 5% of its current age. Here's where things got uncomfortable. The light from those galaxies told a story the models weren't expecting. Their redshift numbers placed them at the right distance, deep in the early universe. But their size and brightness said something else entirely. These weren't small, rough, half-built galaxies. They looked structured, complete, enormous. To understand why that broke the rules, you need to understand what scientists thought the early universe looked like. They had a precise timeline, a detailed map of how everything was supposed to form, step by step, from the first second after the Big Bang. That timeline is called the Standard Model of Cosmology. Scientists spent decades building it. They trusted it completely. Webb just walked in and started asking hard questions about every single chapter of it. What happened next in that data was something nobody had a clean answer for. 13.8 billion years ago, everything that exists compressed into a single point smaller than the period at the end of this sentence. Then it exploded outward. Scientists call that moment the Big Bang, and everything that followed happened in a very specific order according to the models we've built. In the first second, the universe was a boiling soup of particles. Protons, neutrons, electrons, all crashing into each other at unimaginable temperatures. No atoms yet, no structure, just raw energy and chaos. After about 3 minutes, things cooled enough for protons and neutrons to stick together and form the cores of the first atoms, mostly hydrogen and helium. But the universe was still too hot and dense for electrons to join them. The whole thing was like a thick fog, so packed with energy that light couldn't travel through it at all. Then, after about 380,000 years, the temperature dropped enough for electrons to finally attach to those atomic cores. Atoms formed, and suddenly, light could move freely. That first burst of free light is still traveling through the universe today. We call it the cosmic microwave background, and satellites have mapped it in detail. It looks like a faint, even glow coming from every direction in the sky. After that, the universe went dark. For hundreds of millions of years, there were no stars, no galaxies, and no light sources at all. Just hydrogen and helium gas, slowly drifting in clouds, pulled together grain by gravity. According to the Standard Model, the first stars didn't switch on until somewhere between 100 million and 200 million years after the Big Bang. These stars were monsters. They contained hundreds of times more mass than our Sun. They burned so hot and fast they exploded within a few million years, scattering the first heavy elements into the universe: iron, carbon, oxygen. Before these stars exploded, those elements didn't exist anywhere. The The first galaxies came next. Small groups of stars pulled together by gravity. Then those small galaxies slowly merged with each other over billions of years, building larger and larger structures. Our own Milky Way, with its 200 billion stars, took billions of years to reach its current size through countless mergers. That's the timeline. Patient, slow, building from tiny to enormous over billions of years. Webb's job was to look at the earliest chapters of that story and confirm the details. Scientists expected to catch galaxies in the middle of their messy early stages. Small blobs of light, chaotic and dim, just getting started. The first results came in during 2022. Researchers at the University of Edinburgh found 6 galaxies in Webb's early data that were so massive, so fully formed, they had no place in the standard timeline. One of them contained as many stars as the Milky Way does today, and it existed when the universe was only 3% of its current age. According to every model scientists had built, that galaxy should have needed billions more years to form. One researcher told a reporter it was like finding a full-grown adult inside a nursery. The math simply didn't allow for it, and that was just the first batch of data. Webb had only been running for a few weeks. What it found next hit even harder. On July 12, 2022, NASA released Webb's first official science image to the world. The President of the United States stood in the White House to unveil it. That alone tells you how big a moment it was. The image showed a cluster of galaxies called SMACS 0723, sitting about 4 billion light-years from Earth. But the cluster itself wasn't the story. Behind it, stretched and warped around its edges, like light bending through a glass marble, were hundreds of even more distant galaxies. Some of them were so far away that their light took over 13 billion years to reach Webb's mirror. The bending is real. It's called gravitational lensing. Massive objects like galaxy clusters bend the fabric of space around them, and light follows those curves. The cluster acts like a cosmic magnifying glass, stretching and brightening the galaxies behind it so Webb could see things that would otherwise be invisible. Without that lensing effect, the most distant galaxies in the image would have been far too faint for even Webb to detect. Scientists spent the first weeks after release just cataloging what they saw. Teams from dozens of universities downloaded the data the same day it was released, and then the emails started. Astronomers around the world, working independently, kept flagging the same problem. The galaxies in the background weren't behaving the way the models predicted. Some of them looked too bright, too structured, too big for their age. One team calculated the mass of a galaxy sitting at a redshift of about 7, meaning it existed roughly 700 million years after the Big Bang. The result came back and they ran it again. Then again. Then the galaxy had roughly the same mass as the Milky Way. A galaxy that age should have had a fraction of that mass. Building that many stars in that shorter time would require a rate of star formation so extreme that no known process could explain it. Another team found a galaxy that appeared to have already stopped forming new stars. Galaxies stop forming stars when something shuts off their supply of cold gas, usually after billions of years of evolution. This one had apparently gone through that entire process in under 1 billion years. That's like watching a construction crew build a skyscraper and then retire, all in the time it takes most builders to finish the foundation. The deep field image also revealed something about scale that's hard to process. That tiny patch of sky Webb photographed was so small that if you held a grain of sand at arm's length against the night sky, you'd be covering more area than Webb observed. Inside that grain of sand slice of the universe, thousands of galaxies, each one containing hundreds of billions of stars, each star potentially with planets orbiting it. The sheer number of galaxies visible in that image pushed scientists to revise upward the estimated total number of galaxies in the observable universe, from 200 billion to potentially 2 trillion. 2 trillion galaxies, and the early ones weren't cooperating with the models. Astronomers needed a single, definitive example. One galaxy so ancient, so massive, so clearly impossible by the standard timeline that it couldn't be explained away as measurement error or a fluke of lensing. They wanted a result so clean that no one could argue their way around it. They wanted the smoking gun. They were about to find it, and when they did, the redshift number it carried, and the age that number implied, would shake the entire field in a way that still hasn't been resolved. In May 2024, a team of astronomers announced the most distant galaxy ever confirmed. They called it JADESGSZ 140. The name is a catalog label, so let's just call it what it really is: the oldest known light source in the universe. Its redshift number came back at 14.32. Run that through the math, and it places this galaxy at a time just 290 million years after the Big Bang. The universe back then was less than 2% of its current age. A toddler, cosmically speaking. Scientists expected a faint smudge, a handful of early stars just barely clumped together. What they got was something that broke the measurement tools twice before the team believed the results. This galaxy is roughly 1,600 light-years across. For comparison, that's larger than the region of our own Milky Way, where most of the new star formation happens today. A galaxy at 290 million years old shouldn't even be a galaxy yet, according to standard timelines. It should be a cloud of hydrogen gas with maybe a few million stars scattered through it. Instead, it had hundreds of millions of stars already burning. The team measured its brightness and calculated the mass of stars it must contain to shine that intensely. The number was staggering, more stellar mass than 500 million of our suns, packed into a structure that had less than 300 million years to assemble itself from raw gas. To form that many stars that fast, the galaxy would have needed to convert enormous amounts of hydrogen gas into stars at a rate roughly 10 times faster than any star formation rate observed in galaxies today. That's not slightly faster. That's a completely different category of intensity. And the galaxy wasn't just heavy, it was chemically mature. The light Webb captured contained signatures of oxygen and other heavy elements. Here's why that's strange. Oxygen doesn't come from the Big Bang. The Big Bang produced only hydrogen, helium, and tiny traces of lithium. Everything heavier than that gets forged inside stars and scattered when those stars explode. To have detectable oxygen, a galaxy needs at least one full generation of massive stars to have already been born, lived fast, and died violently. At 290 million years old, this galaxy had already gone through that entire first generation of stars. It had formed, exploded its first stars, been enriched with heavy elements, and was now building its second generation, all in a window of time shorter than the gap between today and when the dinosaurs were alive. Every step of that process, according to standard models, should take billions of years. Multiple overlapping steps, each waiting on the previous one. The galaxy JADESGSZ 140 seemed to have skipped several of those steps entirely, or run through them at a speed that current physics struggles to explain. Scientists confirmed the measurements using two independent instruments on Webb. The numbers held, and across the astronomy world, the same question kept surfacing. If one galaxy can do this, how many others are out there, hiding just beyond what Webb has looked at so far? The answer to that depends entirely on one measurement. A measurement that turns out to be far more complicated than it sounds. Every galaxy Webb photographs carries a secret inside its light, a code that tells astronomers exactly how old that light is and how far it's traveled. That code is called redshift, and understanding it is the key to everything that follows. Start with sound. When an ambulance drives toward you, the siren sounds higher pitched. When it drives away, the pitch drops. The sound waves get compressed when the source moves toward you and stretched when it moves away. You can hear the difference without any instruments. Scientists call this the Doppler effect. Light does the same thing. When a star or galaxy moves away from you, the light waves it sends out get stretched. Stretched light shifts toward the red end of the spectrum, hence the name redshift. The faster something moves away, the more its light shifts toward red. The more stretched the light, the higher the redshift number. Now here's where it gets wild. The universe isn't just full of galaxies moving away from us. Space itself is expanding. Everything in the universe is moving away from everything else. And the farther away a galaxy is, the faster it appears to be moving, because more expanding space sits between us and it. So the most distant galaxies in the universe have the highest redshift numbers, because their light has been stretching across expanding space for the longest time. Astronomers measure redshift by looking for specific chemical signatures in a galaxy's light. Hydrogen, for example, absorbs light at very specific wavelengths. Scientists know exactly what those wavelengths look like up close. When they look at a distant galaxy, those same hydrogen signatures appear, but shifted toward red. By measuring exactly how far they've shifted, scientists can calculate a precise redshift number. From that number, they work backwards to figure out how long the light was traveling, which tells them when the galaxy existed. The system is remarkably reliable. Webb's instruments can measure redshifts with extreme precision, picking up chemical signatures in galaxies so faint that Hubble couldn't even detect them as blurry dots. But here's the catch that matters for everything Webb found. Redshift measurements assume we know how fast the universe is expanding. That rate is called the Hubble constant. Scientists plug that number into the formula to convert redshift into distance and age. Change the Hubble constant, and every single distance and age calculation in cosmology changes with it. And right now, astronomers are in the middle of a serious disagreement about what the Hubble constant actually is. Two different methods of measuring it keep giving two different answers. The gap between those answers is small enough to seem boring, but large enough to be a genuine crisis in physics. Some researchers think it's just a measurement error that will get corrected. Others think the gap is telling us something real, that the universe is expanding faster than the standard model predicts, which would mean the universe is younger than we calculated, which would make those impossible ancient galaxies even more impossible. The tool scientists use to date everything Webb sees is built on a number that might be wrong. That's the kind of problem that keeps cosmologists awake at 3 in the morning. The mass problem in those early galaxies gets stranger still, because it's not just about how old they are, it's about how much they weigh. Imagine you're watching a skyscraper get built. You check on it every week. You know exactly how many workers are on site, how many bricks get laid per day, how long each floor takes to complete. After a month, you walk past, and it's already 100 stories tall, fully furnished, with people living on every floor. You'd know something went wrong with your timeline. That's the mass problem Webb uncovered. After the Big Bang, the universe contained a fixed amount of matter. That matter was mostly hydrogen and helium gas, spread out across space in a slightly uneven pattern. Gravity slowly pulled the denser patches together. Over millions of years, the gas collapsed into clouds. Inside those clouds, the first stars ignited. Stars died and made new stars. Stars clustered into galaxies. Galaxies merged into larger galaxies. The whole process works like a chain, and each link takes time. You can't skip steps, because each one depends on the one before it. You can't have a billion stars before you have the gas clouds that form them. You can't have a massive galaxy before the smaller pieces merge to build it. Scientists built detailed computer simulations of this process. They ran them on supercomputers, testing millions of variations. The simulations agreed a galaxy with the mass of our Milky Way needed somewhere between 7 and 10 billion years to accumulate that much stellar mass. The universe had to build it piece by piece, merger by merger, over cosmic timescales. Webb found galaxies with Milky Way scale mass that existed when the universe was only 3 to 500 million years old. That's roughly 4% of the time those simulations required. The building was already finished before the construction crew had even arrived. And the surprise wasn't 1 or 2 galaxies. In a survey called the JADES project, Webb's team found dozens of massive galaxies in the early universe. More than expected by a factor of 10 to 100 times. depending on which mass range you look at, 10 times more massive early galaxies than the best computer models predicted. In some mass categories, 100 times more. Not a rounding error, a systematic overabundance with no clean explanation. That's a systematic problem. A single galaxy being heavier than expected could be a fluke, a weird case, a measurement error. Dozens of them, consistently heavier than every model allows, points to something wrong with the model itself. The simulations might be missing a process. Maybe star formation in the early universe operated differently than it does today, turning gas into stars far more efficiently. Maybe dark matter, the invisible scaffolding that makes up most of the universe's mass, clumped together faster than predicted, giving gravity more to work with earlier than the models assumed. Or maybe the timeline itself is off. If the universe is older than 13.8 billion years, those galaxies had more time to build themselves. That would ease the mass problem without changing any of the physics. But changing the age of the universe means changing one of the most carefully measured numbers in all of science. Some researchers are already asking whether that's exactly what needs to happen. Others argue the age of the universe is settled science, supported by multiple independent measurements, and that changing it would require overturning far more than just the galaxy formation models. The debate is ongoing, and here's what makes the mass problem even harder to dismiss. The galaxies aren't just too heavy, they're shining too bright. The two problems reinforce each other and together point at something specific that no one has fully explained. A candle in a dark room looks bright. Put that candle next to a bonfire, and it disappears. Brightness is relative, and in astronomy, how bright something looks tells you how much energy it's pumping out, which tells you how many stars are burning inside it. When Webb photographed the early universe, the galaxies it found weren't just too massive, they were too luminous. They were pumping out light at rates that made scientists question their instruments before they questioned their models. In galaxies today, star formation runs at a certain speed. Our Milky Way makes roughly 1 to 3 new stars per year. That sounds low, but it's been running for 10 billion years and built 200 billion stars. The process is slow and steady. In the early galaxies Webb found, scientists calculated star formation rates that hit hundreds or even thousands of new stars per year. Running those numbers back in time, a galaxy forming 1,000 new stars per year for a few 100 million years would build stellar mass so fast it defies the constraints of known physics. Here's the specific problem. To form a star, you need a dense, cold cloud of gas to collapse under its own gravity. The cloud falls inward, heats up at the center, and ignites nuclear fusion, but as stars form, they heat the surrounding gas. Hot gas expands and pushes outward. That pushback, called stellar feedback, acts like a natural brake on star formation. It prevents all the gas from collapsing at once. Every simulation of galaxy formation includes that brake. It's a measured, confirmed process observed in galaxies across the nearby universe, and it places a hard ceiling on how fast any galaxy can build stars. Early galaxies were apparently operating well above that ceiling. Astronomers double-checked the brightness measurements using multiple instruments. The results held. One possibility scientists are examining is that the very first generation of stars worked differently. Those stars, which scientists call population 3 stars, formed from pure hydrogen and helium with no heavy elements mixed in. Heavier elements make gas cool faster, and cooler gas fragments into smaller, more numerous clumps. Gas with no heavy elements might form fewer but far more massive stars, each one pumping out so much energy that it strips the braking process away and lets the galaxy run at full speed. Another possibility is that early black holes played a role nobody expected. If supermassive black holes existed early enough and grew fast enough, they could have compressed surrounding gas into star-forming regions with far more efficiency than gravity alone. That would require black holes appearing on a timeline that's also impossible by standard models. Both of those possibilities feed into each other, and both of them are unsolved. The brightness Webb is measuring in these early galaxies isn't just a curiosity, it's a diagnostic. It's the universe telling us that something in the machine of early cosmic evolution was running at a completely different setting than the one we coded into every simulation, textbook, and theory we've built over the last 50 years. And the machine those theories are all built on, the standard model of cosmology, is starting to show cracks in more than one place. The mass problem and the brightness problem aren't isolated glitches. They're symptoms pointing at the same underlying cause. Understanding that cause means looking closely at the rulebook itself, the framework scientists built the entire history of the universe inside of, and asking how solid its foundations really are. Physics has a rulebook. It's called the Standard Model of Cosmology, and for about 30 years, it was one of the most successful scientific frameworks ever built. It explained the Big Bang, predicted the cosmic microwave background, described the large-scale structure of the universe, and accurately forecast how galaxies form and evolve. The model rests on a few core ingredients. Normal matter, the stuff atoms are made of, makes up about 5% of the universe. Dark matter, an invisible form of matter that doesn't emit or absorb light, makes up about 27%. And the remaining 68% is something called dark energy, a force built into the fabric of space that drives the universe's expansion to accelerate over time. With those three ingredients and a set of mathematical equations, scientists could simulate the entire history of the universe from the Big Bang to today. The simulations matched observations across dozens of different tests. Telescope surveys confirmed the predicted distribution of galaxies across space. Measurements of the cosmic microwave background matched the model's predictions to extraordinary precision. For decades, every new observation fit neatly into the framework. Then Webb switched on. The early galaxy problem isn't the only crack. It's the newest and most dramatic one. But physicists had already been watching smaller fractures appear in the standard model for years. The model predicts a specific number for how many dwarf galaxies should orbit the Milky Way. Observations keep finding fewer than predicted. The model describes how dark matter should cluster in the centers of galaxies, building dense spikes. Observations of actual galactic centers show flatter profiles instead, small mismatches, stubbornly consistent across many galaxies and many years of data. Then there's the problem of cosmic structure. The model predicts that at the very largest scales, the universe should look roughly the same in every direction, smooth and even when you zoom out far enough. But surveys keep finding massive structures, long chains and walls of galaxies that appear bigger than the model allows. One structure, discovered in 2022, stretches roughly 3.3 billion light-years across. Scientists named it the Giant Arc. For comparison, the entire observable universe is about 93 billion light-years wide. A single connected structure spanning 3.5% of the observable universe pushes hard against the theoretical limit for how large any structure can grow given the age and expansion rate of the universe. The standard model says structures that large simply shouldn't exist yet. The Giant Arc does exist, and it's not alone. Each individual crack could be explained away on its own. A missing dwarf galaxy here, an oversized structure there. Measurement errors happen. Models get refined over time without requiring a complete overhaul, but the cracks are piling up across unrelated measurements, and that pattern is harder to dismiss. And with Webb's early galaxy data stacked on top, scientists are facing a pattern that's becoming hard to dismiss. Some researchers say the standard model needs a patch, a small adjustment to one of its parameters. Others say the cracks point to something deeper, a fundamental ingredient the model is missing. And a third camp is asking whether one of the model's core measurements, the expansion rate of the universe, is actually wrong. That measurement is called the Hubble constant, and its story is one of the most unsettling disputes in modern science. In science, when two independent experiments measure the same thing and get the same answer, you trust it. When they get different answers, you check for errors. When you check everything twice and they still disagree, you have a crisis. That's the Hubble tension. Edwin Hubble discovered in the 1920s that galaxies outside our own are moving away from us, and the farther away they are, the faster they're moving. This was the first direct evidence that the universe is expanding. The rate of that expansion is now called the Hubble constant. Measuring it should be simple in principle. Watch how fast distant galaxies are moving away, compare that to their distance, and divide. The number you get describes how fast the universe is expanding per unit of distance, meaning for every extra 3.2 million light-years of distance between two galaxies, they're moving apart faster by a set amount. The problem is that astronomers have two separate, completely independent ways to measure the Hubble constant, and they keep getting different answers. Method 1 works in the nearby universe. Scientists use a chain of distance measurements, starting with nearby stars whose distances can be calculated geometrically, then stepping out to brighter and brighter objects they can see further away. At the end of that chain, they measure the speed of distant galaxies and calculate the Hubble constant. Multiple independent teams using this method, using different types of distance markers and different telescopes, consistently land on a value of around 73. Method 2 works by looking at the cosmic microwave background, the ancient afterglow of the Big Bang that satellites have mapped in fine detail. Scientists feed that data into the standard model and calculate what the expansion rate should be. That calculation gives a value of around 67. 73 versus 67. The gap looks small, but in cosmology, it's enormous. It's statistically significant enough that the probability of it being a random measurement error is less than 1 in a million. Both methods have been checked, rechecked, and verified by multiple independent teams using different instruments over many years. The disagreement persists every single time. No one has found the error that would make it go away. If method 1 is right, the universe is expanding faster than the standard model predicts. That means the universe might be slightly younger than we calculated, which would make the impossible early galaxy's Webb found even more impossible to explain within the timeline. If method 2 is right, and method 1 has a hidden error, something in our local measurement chain is off in a way that nobody has been able to identify yet. Or, and this is the option that makes cosmologists genuinely uneasy, both methods are right, and the standard model is wrong. If the universe's expansion rate changed at some point in history in a way the model doesn't account for, both measurements could be accurate and both could appear to contradict each other. Physicists have proposed dozens of modifications to fix the Hubble tension. None of them has fully succeeded yet without breaking something else in the model. Webb is now providing data that could help resolve the tension by giving astronomers more precise distance measurements at extreme ranges. But so far, the data is making the tension harder to explain away, not easier. The new measurements keep landing on the higher end of the range, closer to 73 than 67. That's a problem for the standard model, and it compounds every other crack already visible in the framework. And all of it gets harder to explain when you factor in the invisible ingredient that makes up most of the universe's mass. You can't see it. You can't touch it. Instruments don't detect it directly, but take it out of the universe and everything falls apart. Galaxies scatter. Stars don't hold together. The large-scale structure of the cosmos vanishes completely. Dark matter is real. The evidence for it is overwhelming. It comes from the speed at which galaxies rotate, from how galaxy clusters bend light around them, from the pattern of structure across the entire observable universe. Every one of those observations points to the same conclusion. About 85% of all the matter in the universe is invisible, and it behaves differently from everything we can see. The standard model treats dark matter as cold. Cold means it moves slowly compared to the speed of light. Cold, dark matter clumps together under gravity in a predictable way, forming large halos around galaxies and building the cosmic scaffolding that visible matter then falls into. That scaffolding is why galaxies exist at all. Without it, the gas that forms stars would never clump densely enough to light up. Cold, dark matter has passed test after test in the nearby universe. But Webb is now handing scientists a new testing ground, the early universe. And the results are generating a sharp debate. For cold dark matter to explain the massive early galaxies Webb found, it needs to have clumped into large halos extremely fast, far faster than the simulations predict. Some researchers think there's a fix. If dark matter particles interact with each other in ways we haven't modeled, they might clump more efficiently in the high-density conditions of the early universe than standard cold dark matter would. A tiny change to the physics of how dark matter particles interact could produce dramatically faster halo formation without breaking the model's success in the nearby universe. Other researchers are looking at an alternative called warm dark matter. Warm dark matter particles move faster than cold dark matter, and that extra speed changes how they clump. Instead of building large halos first and then fragmenting into smaller structures, warm dark matter would build structures from the top down. The first clumps would be large. That could potentially explain why early galaxies are already so massive. But warm dark matter has its own problems. It predicts fewer small galaxies than we observe, and it changes the structure of galactic centers in ways that don't quite match observations either. There's a third option that's gaining traction in a small but serious corner of astrophysics. What if dark matter decays? If dark matter particles slowly convert into ordinary matter or radiation over billions of years, the early universe would have had more dark matter than the present one. More dark matter means faster structure formation. The galaxies Webb found might have had extra scaffolding to build on in the early universe, scaffolding that has since disappeared. Each of these possibilities requires modifying a model that has been extremely well tested. That's a high bar. Scientists don't abandon working models without extraordinary evidence. But the extraordinary evidence is stacking up, and all of it, the dark matter debate, the mass problem, the brightness crisis, every thread leads back to a single population of stars. Stars that no one has ever directly seen. Stars that may be lurking just at the edge of what Webb can detect. The universe's very first generation. Before any galaxy existed, there were only gas clouds. Enormous, dark rivers of hydrogen and helium floating through a universe with no light sources at all. The cosmic dark ages lasted hundreds of millions of years. Nothing burned, nothing shone. Space was genuinely dark from one end of the observable universe to the other. Then gravity did what it always does. It pulled. The gas clouds weren't perfectly smooth. Some patches were slightly denser than others, leftovers from the uneven expansion after the Big Bang. Gravity amplified those differences slowly. Dense patches pulled in more gas. The gas compressed. The center heated up. And somewhere in that darkness, after enough time and enough pressure, nuclear fusion ignited. The first star switched on. Scientists call this generation of stars Population 3. No human has ever observed one directly. No telescope has captured their light. Everything we know about them comes from calculations, simulations, and the chemical fingerprints they left behind in the next generation of stars. But those fingerprints paint a picture of something almost monstrous by modern standards. Population. 3 stars formed from pure hydrogen and helium, with 0 heavy elements in the mix. Heavy elements act like a coolant in gas clouds, helping them shed heat and fragment into smaller clumps. Without them, the gas cloud stays hotter longer, and a hotter cloud forms fewer, heavier stars. The models suggest Population 3 stars may have reached masses of 100 to 1,000 times that of our Sunday. Some estimates push even higher. These stars would have been so massive and so hot that they burned through their entire hydrogen fuel supply in under 1 million years. Our sun will burn for 10 billion years. These stars lived and died in a time frame comparable to a single ice age on Earth. When a star of that mass dies, it goes out violently. The most massive ones collapse directly into black holes, swallowing all their mass without a visible explosion. Stars in a slightly lower mass range exploded as supernovae so powerful they outshone entire galaxies for weeks at a time, and they seeded the surrounding space with the first heavy elements that ever existed anywhere in the universe. Carbon, oxygen, iron, silicon, and more. Elements the universe had never contained before that moment. Those explosions were the starting gun for everything that came after. The heavy elements mixed with fresh hydrogen gas. The next generation of stars, called Population 2 stars, formed from that enriched mixture. They fragmented into smaller, longer-lived stars, more like the ones we see today. Planets formed around some of them. And on at least one of those planets, chemistry eventually arranged itself into something that could look back up at the sky and ask where it all came from. Every atom of iron in your blood was forged inside a star that exploded billions of years ago. Every carbon atom in your DNA traces back to a stellar furnace. Population. 3 stars seeded the universe with the raw material for all of it, and yet they remain invisible to us. Every Population 3 star burned out billions of years before any telescope existed to observe it. Webb was designed in part to change that, or at least get close enough to catch their chemical aftermath. Scientists have been combing through its data for years, searching for the specific light signature that would confirm a Population 3 star's presence in a galaxy's chemistry. What they found was unexpected, even by the standards of a mission that had already delivered surprise after surprise. Hunting for something no one has ever seen requires a different kind of strategy. You can't look for the thing itself, you look for what it left behind. Population. 3 stars burned out billions of years ago. Their light is long gone, but when they exploded, they sprayed heavy elements into the surrounding gas. That gas eventually collapsed into the next generation of stars, carrying those chemical fingerprints with it. By looking at the chemical makeup of the oldest surviving stars in the universe, scientists can read the signature of the Population 3 stars that came before them. It works like forensics. You never find the original source, but you find what it touched. Webb can analyze the chemical composition of ancient galaxies by splitting their light into a spectrum, the same way a prism splits sunlight into a rainbow. Each element in a star's atmosphere absorbs specific wavelengths of light, leaving dark lines in the spectrum. The pattern of those lines is unique to each element, a kind of fingerprint. By reading those fingerprints, scientists can list the chemical ingredients of a galaxy billions of light years away. In early 2023, a team using Webb data identified a galaxy sitting about 13.3 billion light years away and detected something striking in its spectrum. The chemical fingerprint showed an extremely high ratio of carbon to oxygen, along with elevated levels of nitrogen. That particular chemical combination doesn't match any known population of stars that formed after the first generation. The standard stellar populations produce different ratios, but theoretical models of Population 3 stars dying in a particular way, specifically as pulsating supernovae rather than standard explosions, predict almost exactly that carbon to oxygen ratio. The data matched what the models said Population 3 stars should leave behind. Scientists were careful not to claim a direct detection. The galaxy they observed wasn't a single Population 3 star. It was an entire young galaxy whose chemical makeup bore the signature of Population 3 enrichment, meaning the first generation of stars had already lived and died inside it before this galaxy's light set off on its 13 billion year journey to Webb's mirror. That finding placed Population 3 star death at extremely early cosmic times, earlier than many models had assumed, and it deepened a problem already sitting in the data. If the first stars burned out so early, they had very little time to form in the first place, which means star formation had to begin extremely fast after the Big Bang, faster than any model currently allows. A separate Webb observation, announced in 2024, found a bright clump of light inside a very distant galaxy that astronomers couldn't explain with any known stellar population. Its brightness, color, and the specific wavelengths of light it emitted matched the signature scientists had theorized a cluster of Population 3 stars might produce. Extremely massive, extremely hot, extremely short-lived. It's not a confirmed detection yet. The data is consistent with several explanations, but it's the closest anyone has come to seeing the universe's first generation of stars with an actual instrument. And if Population 3 stars are hiding at the edge of Webb's vision, something else is hiding there too. something that grew far faster than stars ever could, something that by all rights shouldn't exist this early at all. Black holes grow by consuming. Gas falls in, gets compressed, heats up to millions of degrees, and radiates energy as it spirals down. The infalling material forms a glowing disk around the black hole before it crosses the point of no return. That disk is so bright it can outshine entire galaxies. Scientists call these active feeding black holes quasars, and they're among the most luminous objects in the universe. The problem Webb keeps finding: quasars in the very early universe that are far too massive to have grown by normal feeding. A black hole has a speed limit on how fast it can eat. As matter falls in and heats up, it blasts out radiation. That radiation pushes back against the infalling gas, slowing the rate of consumption. There's a theoretical maximum called the Eddington limit, the point where the radiation pressure exactly balances the gravitational pull. At that limit, a black hole of a given mass can only grow so fast. Take a black hole that starts as a stellar remnant, the collapsed core of a massive star, with a mass of maybe 100 times that of our Sunday. Feed it at the absolute maximum rate allowed by physics. Run that calculation forward in time. After 500 million years of eating at full speed, you get a black hole with a mass of roughly a few million suns. That's already impressive by human standards. But Webb and observations before it have confirmed supermassive black holes with masses of hundreds of millions to billions of solar masses existing when the universe was only 500 to 700 million years old. Some exceed 1 billion solar masses at ages under a billion years. Feed a stellar mass black hole at the Eddington limit continuously for that long, and the math doesn't produce a billion solar mass black hole. You need either a much larger starting seed, a period of feeding beyond the Eddington limit, or both. Several explanations are being explored. The first is direct collapse. Instead of starting as a stellar black hole, some early black holes may have formed when enormous gas clouds collapsed directly into black holes without ever passing through a star phase. That would give them a starting mass of 100,000 or even a million solar masses, a much better head start. The second is that some black holes fed faster than the Eddington limit allows, at least briefly. This is theoretically possible under specific conditions, where the gas falls in so fast that radiation can't escape sideways quickly enough to slow the process. Some simulations have shown this super Eddington feeding can occur in short bursts. Webb is actively detecting these early quasars and measuring their masses with more precision than any previous telescope achieved. In 2023, Webb confirmed the most distant quasar ever detected, sitting at a time just over 600 million years after the Big Bang, with a black hole mass of hundreds of millions of solar masses. The existence of that object sitting at that distance and at that mass pushes the formation problem even harder. Whatever process produced these monsters, it worked at a speed that nothing in our current models fully accounts for. And these black holes weren't just sitting alone in empty space. They lived inside galaxies. And the galaxies they lived in were threaded together by something invisible, the largest structure in the universe. A structure scientists spent decades theorizing about. Webb just found it. 700 million years. In human terms, that sounds like a long time. Longer than complex animal life has existed on Earth. Longer than the dinosaurs, longer than anything we can personally relate to. In cosmic terms, it's nothing. The universe is 13.8 billion years old, 700 million years into its existence. The universe had used up only 5% of the time it's had since then. The Milky Way didn't exist yet. Our sun wouldn't form for another 9 billion years. Earth was 9.5 billion years from existing. And at that incredibly early moment, a black hole had already reached 1 billion solar masses. Scientists first confirmed this in observations made before Webb, but Webb has since measured similar objects with far greater precision. These billion solar mass black holes are called ultramassive black holes, and finding them in the first 5% of cosmic history is the equivalent of finding a fully built aircraft carrier inside a warehouse that opened last week. The numbers make the problem concrete. A stellar black hole formed from a population 3-star collapse might begin with a mass of several hundred solar masses. To reach 1 billion solar masses in 700 million years through Eddington limited feeding alone is mathematically impossible. The math produces a maximum of a few million solar masses over that time. You're short by a factor of hundreds. The direct collapse model helps, but doesn't fully close the gap. Even a gas cloud collapsing directly into a black hole with a starting mass of 1 million solar masses still needs to grow by a factor of 1,000 in 700 million years. Sustained Eddington limited feeding gets you to maybe tens of millions of solar masses. Something else had to be happening. One model suggests these black holes went through phases of extreme feeding, consuming gas at several times the Eddington rate for short, intense periods. Computer simulations have shown this is physically plausible when a black hole sits inside a dense gas cloud with no nearby energy source to heat the gas and create pressure. In the early universe, those dense, cold gas clouds were everywhere. The universe was smaller and more tightly packed. The conditions for extreme feeding may have been common. Another model takes a more radical approach. Maybe the first black holes weren't stellar remnants at all. Maybe they formed from quantum fluctuations during cosmic inflation, the rapid expansion phase that occurred in the first fraction of a second after the Big Bang. These would be called primordial black holes, and if they existed, they could have started with enormous masses from the very beginning. Skipping the growth problem entirely, primordial black holes are still a theoretical concept. Webb data, so far, hasn't confirmed or ruled them out. But the ultramassive black holes in the early universe are so hard to explain with conventional mechanisms that primordial formation is being taken seriously by researchers who would have dismissed it a decade ago. What all of these black holes had in common was their environment. They all sat inside galaxies, which sat inside galaxy clusters, which were woven together by something that existed before any of them. A vast, invisible skeleton stretching across the entire universe. For decades, it existed only in equations. Webb changed that. Zoom out far enough from the universe, and the galaxies stop looking random. They arrange themselves into something that looks almost biological. Long, bright filaments connecting at dense nodes with enormous dark voids in between. Scientists call this arrangement the cosmic web, and it's the largest structure in the universe. The filaments are made of dark matter. That invisible scaffolding formed first, pulling normal matter in along its structure. Gas fell along the filaments, pooled at the nodes, and built galaxies there. The nodes are where the largest galaxy clusters sit today. The filaments connecting them contain long chains of smaller galaxies. The voids between them are nearly empty, giant bubbles of space with very little matter at all. The cosmic web covers the entire observable universe. Every galaxy that has ever existed sits somewhere in that structure, shaped by it, held in place by it, fed by it. The Milky Way sits in a relatively quiet region, connected to a cluster of a few dozen galaxies called the local group, which itself connects to a much larger supercluster of thousands of galaxies. For decades, scientists confirmed the cosmic web by mapping the positions of millions of galaxies across the nearby universe. The pattern was clear, but the individual filaments themselves, the dark matter threads that hold it all together, were nearly impossible to image directly. Dark matter doesn't emit light. You can only infer its presence from the way it bends light and pulls on visible matter. Seeing the filaments directly required catching normal matter as it moved along them. In 2019, a team used background quasar light to illuminate a filament connecting two galaxy clusters and captured the first direct image of a cosmic web filament in visible gas. But it was fuzzy, indirect, and required extreme conditions to capture. Webb changed the resolution of the problem entirely. Because Webb can peer into the very early universe, it can watch the cosmic web as it was forming. In the early universe, the filaments were denser, brighter, and more actively channeling gas into forming galaxies. The matter flowing along them was still glowing with the heat of recent collapse. That makes the filaments detectable in ways that the evolved, quiet filaments of the modern universe are not. Webb observations in 2023 found a group of very early galaxies arranged in a pattern that precisely traced the expected location of a large dark matter filament sitting about 13 billion years ago. The galaxies formed a line, evenly spaced, each one sitting at a dense point where gas flowing along the filament would have pooled. The arrangement matched simulations of filament formation so well that the team concluded they had mapped a section of the cosmic web at a time when the universe was less than 1 billion years old. That's the earliest direct map of cosmic web structure ever produced, and it raised a question that sends a chill through the standard timeline. If the cosmic web was already this developed less than 1 billion years after the Big Bang, it must have formed extremely fast, faster than the models say dark matter can clump and arrange itself, which means dark matter, the foundation of all structure in the universe, may have properties we haven't accounted for yet. And if the scaffolding of the universe formed faster than we thought, then what it built inside itself, the galaxies, the stars, and the black holes, had far more time to grow than the standard timeline allows. The next puzzle is what those early galaxies did with that extra time, because one of the first things they accomplished was something that changed the entire universe forever. After the Big Bang, the universe spent its first 380,000 years as an impenetrable fog. Then atoms formed, and light could finally travel. The cosmic microwave background was that first burst of free light. But what followed was a second kind of darkness, less dense than the original fog, but still enough to block certain kinds of light from traveling freely through the universe. When atoms formed, they were neutral. Neutral hydrogen is extremely good at absorbing ultraviolet light. The early universe, filled with neutral hydrogen gas between the first galaxies, acted like a filter. Ultraviolet photons couldn't travel more than a short distance before getting absorbed. The universe was transparent to visible light, but opaque to the kind of energetic light that stars produce most intensely. Then the first galaxies switched on. Their stars pumped out massive amounts of ultraviolet radiation. That radiation hit the surrounding neutral hydrogen and ripped the electrons away from the atoms, a process called ionization. The regions around the first galaxies became bubbles of ionized gas, transparent and clear. As more galaxies formed and more stars ignited, those bubbles grew and merged. Over several 100 million years, the entire universe transitioned from a universe filled with neutral hydrogen to a universe filled with ionized hydrogen, transparent in all directions. This process is called reionization, and it's one of the most important chapters in cosmic history. Without it, the universe would have remained foggy, and most light would have struggled to travel freely. Scientists have known about reionization for decades. They had rough timelines for when it happened and some idea of what drove it. But the details were blurry. How fast did it happen? Which galaxies contributed the most? Did large, bright galaxies do most of the work, or was it the countless small, dim ones? Webb answered some of those questions and opened new ones. In observations of galaxies sitting in the reionization era, roughly 500 to 900 million years after the Big Bang, Webb detected something subtle but significant. The amount of ionizing radiation escaping from these galaxies was higher than expected. A larger fraction of the energetic photons the galaxies produced was actually getting out into the surrounding gas rather than being absorbed internally. That means early galaxies were more efficient at driving reionization than previous models assumed. They punched through the surrounding gas more effectively, and if they drove reionization faster, then the universe became transparent earlier than previously thought. An earlier reionization means the universe opened up for galaxy formation earlier than the standard timeline assumed. More transparent space means more room for structure to grow. That feeds back into the mass problem and the brightness problem Webb already uncovered. Every discovery is connected, but there's a twist. Webb also found that some of the brightest early galaxies sit in patches of the sky that are still partially neutral, surrounded by hydrogen fog that their radiation hasn't fully burned away yet. That means reionization was uneven. It didn't sweep across the universe smoothly like a wave. It happened in patches, some regions going transparent, while nearby regions stayed foggy for millions of years longer. That uneven pattern means the timeline of early galaxy formation is even more complicated than the models suggested. Some regions had more time, others had less. The universe didn't build itself on a single schedule, and somewhere in all of that uneven early growth, an enormous amount of ordinary matter went missing. Scientists know exactly how much there should be. For decades, they couldn't find it. Webb just got the closest look yet at where it might be hiding. Physics has an accounting problem. Scientists know exactly how much normal matter the universe should contain. They calculated it from the cosmic microwave background, from measurements of how light elements formed in the minutes after the Big Bang, and from the large-scale structure of the cosmos. The number is precise and well-tested. Normal matter, the stuff that makes up atoms, planets, stars, and every living thing, adds up to about 5% of the total content of the universe. That might sound small, but the universe is unimaginably large. 5% of everything that exists is an enormous amount of material. The problem is that for decades, when astronomers added up all the normal matter they could actually observe in stars, galaxies, gas clouds, and galaxy clusters, they came up roughly 40% short. 40% of all the atoms in the universe were simply unaccounted for. Astronomers called this the missing baryon problem, using the technical word for the type of particles that make up ordinary matter. This wasn't a small rounding error. It was a gaping hole in the cosmic inventory. Scientists knew the matter had to be somewhere. The Big Bang physics that predicted its total amount is among the most tested and reliable in all of science. The matter existed. It just wasn't showing up where anyone was looking. The leading theory, developed through computer simulations in the early 2000s, predicted that the missing matter hides in the cosmic web, specifically in the warm gas that fills the long filaments connecting galaxy clusters. This gas is too hot to condense into stars, but too cool to emit X-rays that satellites could easily detect. It sits in a temperature range that makes it nearly invisible to conventional observatories. Simulations showed that somewhere between 40 and 50% of all normal matter in the universe should be hiding in those filamentary structures, strung out across the cosmic web in thin sheets and threads. But detecting it directly required either extraordinarily sensitive instruments or a lucky alignment of distant bright objects that could illuminate the gas from behind. Webb added a new tool to that search. By analyzing the light from distant quasars as it passes through regions where filaments should exist, Webb's spectrographs can detect the chemical signatures of warm gas that previous telescopes couldn't resolve. In 2023, a team using Webb data found clear chemical signatures of warm gas sitting along a cosmic Webb filament in the early universe, in a location and at a density that matched the simulations of where the missing matter should be. It was a partial detection, covering only a slice of one filament at one point in cosmic history. But the match between the observation and the prediction was close enough that it pointed directly at the filaments as the hiding place. If that picture is correct, the missing baryon problem is close to solved. The matter was always there, invisible in the scaffolding of the cosmic web, waiting for an instrument sensitive enough to catch its faint chemical glow. But catching missing matter in the present universe is straightforward compared to what Webb has been doing at the other end of cosmic history. Because, in the very early universe, galaxies weren't calmly sitting in their filaments. They were crashing into each other. And the collisions Webb found were happening earlier than any model said was possible. Two galaxies colliding looks dramatic, but it happens in slow motion. The process takes hundreds of millions of years from first contact to final merger. Gravity pulls the two systems toward each other. They pass through each other, stars and gas mix. Spiral arms stretch and warp, and eventually the combined mass settles into a single larger galaxy. The Milky Way is heading toward its own collision. The Andromeda Galaxy sits about 2.5 million light-years away and is moving toward us at about 70 miles per second. In about 4.5 billion years, the two galaxies will collide. Our solar system will survive, since the space between stars is so vast that individual stellar collisions are extremely rare during a galactic merger. But the shape of everything we know as the night sky will be completely rearranged. Galaxy mergers aren't rare in the modern universe. Scientists observe thousands of them, and the Standard Model predicted that in the early universe, mergers should have been even more common, since galaxies were packed into a smaller volume of space, and gravity had more opportunities to bring them together. But the timing of those early mergers in the Standard Model followed a specific pattern. Small galaxies should collide first, building up medium-sized ones. Medium ones then merge to form large ones. The process is hierarchical, bottom-up, and takes billions of years to produce the largest galaxies. Webb is finding mergers between already large galaxies happening far earlier than that hierarchy allows. In 2023, astronomers using Webb identified a system of galaxies in the process of merging at a time just over 700 million years after the Big Bang. The two galaxies in the system were already large, each containing billions of stars. The merger was active, with streams of gas and stars stretched between the two systems. And both galaxies had chemical makeups suggesting they had already gone through multiple generations of star formation before the merger even began. For two large, chemically mature galaxies to be merging at that point in cosmic history, each one would have had to form and evolve at a rate far beyond standard predictions. The model doesn't build galaxies that big that fast, let alone bring two of them close enough to merge. A second Webb study in the same period found a cluster of galaxies in the early universe that showed clear signs of ongoing mergers across the entire group. Multiple pairs were interacting simultaneously. The cluster itself was too dense, too massive, and too well organized for its age. Clusters of that size and structure are supposed to take billions of years to assemble. What makes early mergers specifically important is what they trigger. When two gas-rich galaxies collide, the compression of their gas clouds sets off an explosion of star formation. The collision ignites a starburst, briefly pushing star formation rates to hundreds or thousands of times normal levels. That burst contributes to the brightness problem Webb already found. The unexpected mergers and the impossible brightness feed into each other. And the mergers scattered something across the early universe that the Standard Model says shouldn't have been present yet. Elements that only form deep inside massive stars, after multiple generations of stellar evolution. Finding them this early points at a process in the early universe that nobody fully understands yet. The universe began with a very short ingredient list. Hydrogen made up about 75% of all matter after the Big Bang. Helium made up most of the rest. A tiny trace of lithium came along too. That was the complete inventory of elements in the early universe. Every other element on the periodic table, every atom of carbon, oxygen, iron, gold, uranium, and everything else had to be manufactured later, inside stars. The process works like this. A massive star fuses hydrogen into helium, then helium into carbon, then carbon into oxygen, and so on up the periodic table. Each step requires more temperature and pressure than the last. When the star finally collapses and explodes as a supernova, it scatters those newly made elements into the surrounding gas. That gas eventually collapses into the next generation of stars, carrying the heavy elements with it. The whole cycle has a time requirement. A massive star needs a few million years to form, burn through its fuel, and explode. Then the scattered elements need time to mix into the surrounding gas. Then that gas needs to collapse into new stars, which need time to form. From start to finish, enriching a region of the universe with significant amounts of heavy elements takes at minimum tens of millions of years. And to build up substantial concentrations, it typically takes hundreds of millions to billions of years across multiple stellar generations. Webb has detected oxygen, carbon, neon, and other heavy elements in galaxies that existed less than 300 million years after the Big Bang. The concentrations are lower than in modern galaxies, but they're measurable, they're real, and they require that at least one full generation of massive stars had already been born, burned out, and exploded inside those galaxies before the light Webb captured even left. The enrichment happened on a timeline that leaves almost no room in the standard model for the processes that should have preceded it. In early 2024, one team found a galaxy at a redshift of over 10, placing it within the first 500 million years of cosmic history, with an oxygen abundance higher than many simulations predicted would exist until several billion years after the Big Bang. The galaxy wasn't just old, it was chemically advanced for its age, like finding a teenager who already has the medical history of a 60-year-old. The chemical enrichment problem compounds everything before it. To have oxygen in a galaxy that young, star formation had to begin essentially at the dawn of galaxy formation and run at extreme rates. The first generation of population, 3 stars had to ignite, live, and die, all before 300 million years had passed. And the next generation had to be well underway. That timeline isn't impossible in isolation, but stacked on top of the mass problem, the brightness problem, and the galaxy merger problem, it paints a picture of an early universe operating at a completely different speed than the standard model allows. Some scientists are asking whether the model of how stars die and spread their elements needs revision too. Whether the first supernovae were more powerful, more frequent, or more efficient at dispersing their contents than the physics we use to model modern supernovae. If so, the whole picture of early chemical enrichment would shift across the board, and that shift carries consequences that reach far beyond the early universe. It reshapes the timeline of when the building blocks of planets, and potentially life, first became available across the cosmos. Every atom of gold on Earth came from a catastrophic collision between 2 dead stars. Every atom of calcium in your bones was forged inside a star that exploded hundreds of millions of years before the Sun formed. The process of how stars live, die, and scatter their contents is one of the most studied topics in astrophysics. Scientists have models for it backed by decades of observation, but the early universe is now revealing gaps in those models that nobody anticipated. When a massive star explodes as a supernova, the explosion doesn't scatter elements evenly in all directions. Some material gets flung outward fast and far, mixing into the surrounding gas. Some material collapses back into the stellar remnant and disappears into a black hole or neutron star. The fraction that escapes and how far it travels determines how quickly the surrounding gas gets chemically enriched. In the modern universe, scientists observe supernovae in nearby galaxies and measure the yields, the amounts of each element the explosion releases. Those measurements go into models of chemical enrichment that then get applied to the early universe. The assumption is that early supernovae worked the same way. Webb is now giving astronomers their first close look at the chemical signatures left by the very first supernovae, and some of those signatures don't match modern yields at all. Population, 3 stars, the first generation, were so massive that the mechanics of their explosions may have been fundamentally different. Some models suggest that the most extreme population, 3 stars, died as pair instability supernovae, a type of explosion so powerful it leaves no remnant behind at all. The entire star, core and all, gets blown apart in a single catastrophic event. The energy released in a pair instability supernova can exceed a standard supernova by a factor of 100. Critically, it also scatters a different ratio of elements than a standard supernova does, leaving a unique chemical calling card in the gas it enriches. The specific chemical fingerprints of pair instability supernovae show up in certain ancient stars in the Milky Way that scientists have identified as belonging to the very earliest stellar generations. Webb is now detecting those same unusual chemical ratios in the spectra of distant early galaxies. The pattern is consistent. The first supernovae really were different. more powerful, more complete in their destruction, and far more efficient at spreading enrichment across wide areas. If that's correct, the models scientists use for early chemical enrichment need significant revision. The early universe seeded itself with heavy elements faster than any current simulation accounts for, and that faster seeding accelerates every downstream process: planet formation, the cooling of gas into dense star-forming clouds, and the buildup of complex chemistry in the regions between stars. It also opens a door that scientists have been careful about walking through. If chemical enrichment happened faster than we thought, and if early star formation ran hotter and faster than our models allow, then the conditions for planetary formation and complex chemistry arrived in the universe much earlier than the standard timeline places them. Earlier chemistry means earlier planets. Earlier planets means more time for something to develop on them, and more time means a question that grows harder to ignore with every Webb observation. A question about whether the universe had time to build something extraordinary before Earth even existed, something that might have left a mark we haven't yet learned to read. 13.8 billion years is one of the most precisely measured numbers in science. It comes from multiple independent methods: the age of the oldest stars, the temperature and pattern of the cosmic microwave background, the rate of the universe's expansion, and the abundance of light elements from the Big Bang. All of those measurements converge on the same number, and the precision is remarkable. Scientists place the uncertainty at roughly 1%, so when some researchers started asking whether the universe might actually be older, they weren't doing it casually. They were doing it because the data Webb collected kept producing problems that a slightly older universe would solve. The core issue is what physicists call the age problem in the context of the early galaxies. For the massive, chemically mature galaxies Webb found to exist at 200 to 400 million years after the Big Bang, the universe needs to have given them enough time to form. Squeeze the formation process into the standard timeline, and you need extreme star formation rates that violate known physics. Give those galaxies a few extra 100 million years, or even a billion more years, and the formation rates drop into a range that standard physics can handle. In 2023, a physicist named Rajendra Gupta published a study proposing that when certain adjustments are made to cosmological models involving how physical constants behave across cosmic time, the universe could be as old as 26.7 billion years, double the standard estimate. The paper attracted significant attention and significant criticism in equal measure. Most cosmologists argued the methodology had unresolved problems and conflicted with other well-tested observations. But the fact that a serious peer-reviewed journal published it at all reflects how much pressure Webb's findings are putting on the standard timeline. A few years ago, a paper like that would have struggled to get through review. A less radical proposal doesn't require changing the age of the universe itself, only revising when specific events occurred within it. If dark matter clumped faster than standard models allow, giving early galaxies a denser scaffolding to build on, then galaxy formation could have started earlier within the existing 13.8 billion year framework. The universe stays the same age, but the clock on galaxy formation starts ticking sooner. Some researchers think this is the more likely fix. There's also the Hubble tension to consider. If the universe is expanding faster than the standard model predicts, then working backwards from that faster expansion gives a younger universe, not an older one. A younger universe makes the early galaxy problem worse. Some researchers think reconciling the Hubble tension and the early galaxy problem simultaneously requires changing the physics of the early universe in ways that haven't been fully worked out yet. What all of these possibilities share is a willingness to question parameters that were considered settled. That's uncomfortable for a field where the standard model took decades to build and has passed hundreds of independent tests. Scientists don't abandon working frameworks lightly. The evidence has to be overwhelming. Webb hasn't reached that threshold yet, but it's applying pressure that the field hasn't felt since the discovery of dark energy in the late 1990s. upended the assumption that the universe's expansion was slowing down. And one theory that sat quietly on the fringe of cosmology for decades is now getting a second look from researchers who would have dismissed it 10 years ago. In the 1920s, two competing ideas tried to explain why distant galaxies appear redshifted. The winning idea, the one science settled on, was cosmic expansion. Space itself is stretching, carrying galaxies apart from each other, and that stretching redshifts their light. The expansion is measurable, consistent, and confirmed across dozens of independent observations spanning a century of astronomy. The losing idea came from a physicist named Fritz Zwicky, who proposed something called tired light. His idea was simpler. Light loses energy as it travels through space, gradually shifting toward red over long distances, the way a runner loses speed over a marathon. The red shift we observe, in this view, would have nothing to do with galaxies moving apart. It would just be light getting tired on its long journey across the cosmos. Tired light lost for good reasons, and the reasons were detailed. The theory makes specific predictions about how distant supernovae should appear in time-lapse observations, predictions that directly contradict what astronomers have measured. A supernova in an expanding universe takes longer to fade when viewed at high redshift because time itself is stretched along with the light. Tired light predicts no such stretching, and observations clearly show the stretching is real. The theory also fails to explain the cosmic microwave background the way the Big Bang model does. By the 1980s, most cosmologists had moved on entirely, and the theory fell out of serious discussion for decades. Then Webb found galaxies that appeared too large and too structured for the standard cosmological timeline. And a small but credible group of researchers started asking whether a modified version of the tired light concept, combined with a static or slowly evolving universe, could explain what Webb is seeing without requiring the extreme early galaxy formation rates that are breaking the standard model. In 2023, two physicists published a paper analyzing Webb's early galaxy data against predictions from both the standard model and a modified tired light framework. They concluded that on certain specific measurements related to galaxy surface brightness at high redshift, the tired light model actually fit the Webb data better than the standard Big Bang model did. The paper went through peer review and was published in a legitimate astronomy journal. The backlash from the wider astronomy community was swift and detailed. Other researchers pointed out the analysis had serious weaknesses and that the standard model still outperforms tired light across the full set of cosmological observations. A single good fit on one specific measurement doesn't overturn a framework that passes hundreds of independent tests covering completely different aspects of the universe's history. But the episode revealed something important about where the field stands right now. The fact that a tired light paper could get published in 2023, citing Webb data as motivation, would have been nearly unthinkable in 2015. Webb hasn't validated tired light, but it has cracked open enough questions about the standard timeline that even fringe alternatives are getting a fresh and serious examination from researchers with real credentials. The more mainstream response is to look for modifications to the standard model that preserve its core structure while accommodating what Webb found. Several of those alternatives are now being actively tested with new data, and one of them touches something so fundamental that even describing it requires rethinking what happened in the universe's very first moments. Science moves slowly on purpose. A new theory has to survive dozens of independent tests before it replaces an established one. The standard model of cosmology has survived hundreds of tests over 50 years. Webb's findings haven't destroyed it, but they've pushed a handful of alternative models from the fringe into active research programs at major universities. The first alternative getting serious attention is called early dark energy. In the standard model, dark energy only becomes important in the relatively recent universe, after galaxies have had billions of years to form. Early dark energy proposes that a burst of dark energy also existed in the very early universe, just before and during the period when the cosmic microwave background was imprinted. This burst would have briefly accelerated expansion, changed the scale of density fluctuations, and shifted the timing of structure formation to an earlier point on the cosmic clock. Some versions of early dark energy also help address the Hubble tension by reconciling the two competing expansion rate measurements that are currently producing a gap no one can fully explain. The model predicts a specific set of subtle changes in the cosmic microwave background pattern that satellites are only now becoming sensitive enough to detect. Current data is consistent with early dark energy, but doesn't confirm it yet. Webb's early galaxy findings fit more naturally into a universe where structure formation began slightly earlier than the standard timeline allows, which early dark energy could provide. The second alternative is a modification to inflation, the period of extremely rapid expansion in the universe's first fraction of a second. Standard inflation predicts the density fluctuations that eventually became galaxies were nearly identical in size across all scales. Some modified inflation models predict slightly larger fluctuations on certain scales, giving gravity denser seeds to work with and allowing the first structures to collapse faster than standard inflation allows. A small tweak to the inflation model might resolve the early galaxy problem without requiring any change to dark matter, dark energy, or the age of the universe. The third alternative is more radical. It proposes that dark matter interacts with itself, or with normal matter, in ways the standard cold dark matter model doesn't include. Self-interacting dark matter can form denser clumps under certain conditions, specifically in the high-density environments of the early universe, giving early galaxies more scaffolding to build on and allowing them to assemble faster than the standard model predicts. Several teams have built computer simulations incorporating self-interacting dark matter and found the results produce more massive early galaxies in better agreement with Webb's observations. The tricky part is that any self-interaction strong enough to help in the early universe must be weak enough not to produce visible effects in the nearby universe, where cold, dark matter predictions already match observations closely. None of these alternatives has been confirmed. Each makes predictions that the next generation of observations will test. Webb itself is contributing data that will either support or rule out each one over the coming years. What all three share is a common thread. The early universe was more active, more structured, and more complex than the standard model assumed. Webb didn't break cosmology. It sharpened the question of which version of cosmology is correct. That sharpened question gets stranger when you look at what Webb found inside the very first galaxy clusters. Because clusters that size don't just challenge the formation timeline. They challenge what we thought was possible given the age of the universe. A galaxy cluster is the largest gravitationally bound object in the universe. Hundreds to thousands of galaxies, held together by the combined gravity of their dark matter halos, their stars, their gas, and the superheated plasma that fills the space between them at temperatures of tens of millions of degrees. Building one requires billions of years of mergers, accretion, and gravitational assembly. The Virgo cluster, the nearest large cluster to our own galaxy group, has been assembling for over 10 billion years and still contains regions of ongoing merger activity today. Webb found what appears to be a galaxy cluster in the early universe, at a time when the universe was less than 800 million years old. The structure contained dozens of galaxies concentrated in a small volume of space, all sharing similar velocities and chemical properties that suggest they're gravitationally linked. Several of the galaxies in the group showed signs of active star formation and ongoing mergers between them. A structure like this, at that point in cosmic history, has a serious formation problem. To be gravitationally bound at that age, the galaxies inside it had to have already assembled enough mass to hold each other in place. That mass had to come from somewhere, and the only place it could come from is the standard galaxy building process. Gas collapsing, stars forming, galaxies merging, repeat. The standard timeline places that process at several billion years minimum for a cluster of this size. Finding it at 800 million years doesn't just compress the timeline. It requires that dark matter halos massive enough to host the entire cluster had already collapsed by that point. The collapse of those halos is theoretically the slowest part of the process, since dark matter responds only to gravity and the universe's density fluctuations set the pace. Speeding that up requires either denser initial fluctuations, a different kind of dark matter, or some combination of physics that the standard model doesn't include. Inside the early cluster, Webb detected something even more unexpected. Several of the galaxies showed signs of already being quenched, meaning they had stopped forming new stars entirely. Quenching typically happens when a galaxy runs out of cold gas, which gets consumed by star formation and heated by supernovae and active black holes until it can no longer collapse into new stars. In modern clusters, galaxies quench over billions of years of environmental processing as the cluster's hot gas strips them of their fuel. At 800 million years after the Big Bang, some galaxies inside this early cluster had apparently already gone through their entire active star-forming phase and shut down. The implication is stark. Those galaxies formed all their stars, exhausted their gas supply, and went quiet inside a window of less than a few 100 million years. That's a lifespan so compressed that no standard model accounts for it. Webb is continuing to survey the early universe for more structures like this. Each new detection adds to a pattern that the upcoming generation of telescopes, currently being planned and built, will have to address directly. But the cluster problem isn't the deepest crack in the foundation. For that, scientists have to look somewhere else entirely. At a faint signal left over from the Big Bang itself. A signal with a cold spot that nobody can explain. The cosmic microwave background is the oldest light in the universe. It was released 380,000 years after the Big Bang, when the universe cooled enough for atoms to form and light could finally travel freely. Satellites have mapped it in extraordinary detail. It covers the entire sky, coming from every direction, and it looks almost perfectly uniform. Almost. The temperature of the cosmic microwave background varies slightly across the sky by tiny fractions of a degree. Those tiny variations are the seeds of all the structure that eventually formed. The density differences that gravity amplified into galaxies, clusters, and the cosmic web. The pattern of those variations matches the predictions of the standard model extremely well, except for one region of the sky. In the southern sky, there's a patch of the cosmic microwave background that's measurably colder than the surrounding area, colder by about 70 microkelvin, which is an incredibly small difference but statistically significant enough that it stands out clearly in the data. Scientists have been studying it since it was first clearly identified in the early 2000s. They call it the cold spot. Several explanations have been proposed. The simplest is a statistical fluke. The pattern of the microwave background has a small chance of generating a cold region that large just by chance. The probability is low, somewhere around 1%, not low enough to immediately rule out. Some scientists think it's nothing, and that continuing to study it is chasing noise. But a more dramatic explanation that has survived serious scrutiny involves an enormous supervoid sitting between us and the cold spot. A supervoid is a region of space with far less matter than average. When light from the cosmic microwave background travels through a dense region, it gets a tiny energy boost from the gravitational field it passes through. When it travels through a void, it loses a tiny amount of energy. A large enough void in the right location could produce the apparent cold temperature anomaly we see. Surveys of the galaxy distribution in the cold spot region have found evidence of a large underdense region, though whether it's large enough to fully explain the temperature anomaly is still debated. The connection to Webb's findings comes through the large-scale structure problem. Webb has confirmed that the early universe contained more massive structures, denser clusters, and larger connected systems than the standard model predicts. If the universe formed structure faster and in greater concentrations than expected, It should also have produced larger voids than expected, since the matter that packed into those dense structures had to come from somewhere. Emptier voids and denser clusters go together. The cold spot supervoid, if it's real, would be a logical partner to the oversized structures Webb is finding. If a single supervoid stretching hundreds of millions of light-years across can exist in the nearby universe, and Webb is confirming oversized structures throughout the early universe, both observations point toward the same underlying cause. Structure formation in the universe ran at a different speed and scale than current models allow. The universe built bigger things in more extreme concentrations than the standard recipe predicted. And at the deepest level, that raises a question about what set the recipe in the first place. The Big Bang is where the story starts. That's the assumption embedded in every cosmological model, every computer simulation, every textbook chapter on the origin of the universe. Before the Big Bang, the question of what existed doesn't have a scientific answer because all known physics breaks down at the boundary of that moment. Time itself may not have existed in any meaningful sense before it, and yet, the structure of the early universe, the specific pattern of density fluctuations that seeded all subsequent structure, carries information, and some researchers are asking whether that information points to processes that happened before the bang itself. The cosmic microwave background isn't random. The pattern of its temperature variations has a specific statistical structure. The Standard Model explains that structure through inflation, the rapid expansion phase in the first fraction of a second after the Big Bang, which stretched quantum fluctuations to cosmic scales and imprinted them on the density of the early universe. Inflation works. It explains the pattern well. But inflation also has free parameters, settings that can be adjusted to produce different predictions. The specific values that match observations have to be fed into the model from outside. Inflation doesn't predict its own starting conditions. Something had to set those conditions, and inflation itself doesn't explain what. Several theoretical frameworks propose that inflation was preceded by a contraction phase, a universe that collapsed from a previous state, bounced, and re-expanded. In some of these models, called bouncing cosmologies, the current universe is one cycle in a recurring sequence. Structure from the previous cycle could leave faint imprints in the pattern of the current universe's density fluctuations. Webb is probing the early universe at a level of detail that is starting to put pressure on these theoretical ideas. Certain anomalies in the distribution of early galaxies, the locations of the largest structures, and the specific correlations in the early galaxy clustering patterns are being analyzed for deviations from inflation's predictions. So far, the deviations are small and the data is genuinely ambiguous. But the searches are real, the teams conducting them are serious, and the results are being watched closely across the field. The fact that these searches are being conducted at all reflects how much room Webb's discoveries have opened up for challenging the foundations. A separate thread comes from the primordial gravitational wave background. If inflation happened, it should have produced gravitational waves that still ripple through the universe today. The amplitude of those waves encodes specific information about the energy scale of inflation and the conditions that drove it. Detecting them would confirm inflation at a specific energy. Failing to detect them above a certain level would rule out certain inflation models and potentially favor alternatives. Several experiments are currently hunting for this gravitational wave background in the cosmic microwave background's polarization pattern. Webb isn't involved in that particular search, but the combination of Webb's early galaxy data and those gravitational wave results will together constrain what happened in the universe's first moments, far more tightly than any single observation could alone. If those constraints don't fit inflation cleanly, the door to pre-Big Bang physics opens wider than it has ever been. And right behind that door sits one of the most controversial ideas in all of modern science. An idea that used to live only in theoretical papers and now keeps showing up in conversations about what Webb's impossible galaxies might actually mean. The multiverse is one of those ideas that makes careful scientists uncomfortable. It's hard to test, easy to misuse, and has a long history of showing up in pop science as a catch-all explanation for anything mysterious. Most working cosmologists treat it with caution, but it keeps coming back. And after Webb's findings, some researchers are discussing it in contexts that go beyond theoretical speculation. The multiverse, in its most scientifically grounded form, comes directly out of inflation theory. If inflation drove rapid expansion in the very early universe, the physics of inflation also predicts that it might not have stopped uniformly everywhere. Some regions of space stop inflating and become universes like ours. Other regions keep inflating indefinitely, continuously spawning new bubble universes with their own physical constants and initial conditions. This picture is called eternal inflation, and it emerges from the same equations that predict the universe's observed large-scale structure. In an eternal inflation scenario, the specific values of physical constants in our universe, the strength of gravity, the mass of electrons, the energy of the vacuum, were set by the random conditions of our bubble when it stopped inflating. Different bubbles would have different constants. Some would have constants incompatible with atoms, stars, or life. Others might have constants that allow complex structures to form faster, more efficiently, or in greater abundance than in our universe. Here's where Webb enters the picture. The galaxy's web found forming too fast, building too much mass in too little time, might be telling us that our universe's constants are actually tuned toward faster structure formation than the standard model assumed. If so, the constraints we built into our simulations were based on a misreading of the parameters, and a multiverse framework could explain why those parameters landed where they did without requiring a more fundamental physical mechanism. This is speculative territory. The multiverse makes few predictions that can be directly tested with current instruments. One exception involves bubble collisions. If two inflation bubbles collided early in cosmic history, that collision might have left a faint imprint in the cosmic microwave background, a specific pattern of temperature anomalies in a particular region of the sky. Researchers have looked. The cold spot in the cosmic microwave background has been examined as a candidate bubble collision scar. The analysis is inconclusive. The cold spot is consistent with a bubble collision, but also consistent with other explanations. The signature, predicted by bubble collision models, is subtle enough that current data can't definitively confirm or rule it out. Webb's deeper contribution to the multiverse debate is indirect but meaningful. By showing that the early universe contained structures that strain the known physics of our universe's constants, it raises the probability that at least one of those constants was set to a value different from what standard models assumed. The early galaxy formation rates Webb measured are so extreme that some researchers argue they point to a universe where the efficiency of structure formation is tuned higher than our models predict, possibly reflecting initial conditions drawn from a broader distribution than any single universe model can produce. And if one constant can differ from expectation, the broader framework in which constants vary across universes becomes more, not less, worth investigating carefully. What all of these questions are quietly building toward is a conclusion that reshapes not just cosmology, but the possibility of life itself existing far earlier in cosmic history than anyone previously calculated. Every planet forms from the same raw material, the leftovers from a star's birth. When a cloud of gas and dust collapses to form a star, a disk of material orbits the young star and slowly clumps together into planets. Rocky planets like Earth need heavy elements to form: silicon, iron, oxygen, magnesium. Elements that only exist because earlier generations of stars made them and scattered them through supernova explosions. The standard model placed the first rocky planets at roughly 1 to 2 billion years after the Big Bang, after the first few generations of massive stars had lived and died and enriched the surrounding gas with enough heavy elements to build solid worlds. Webb is finding heavy elements like oxygen and carbon in galaxies that existed less than 500 million years after the Big Bang. If those elements were present in the gas of early galaxies at that age, then the conditions for rocky planet formation arrived much earlier than the standard timeline allows, potentially by several 100 million years. In a universe where planets took billions of years to accumulate habitability, several 100 million extra years is a massive window. What does a rocky planet need to potentially support life? Liquid water, which requires a planet in the right temperature zone around its star. An energy source, either stellar radiation or internal heat from radioactive decay. A stable chemical environment with access to carbon and other key elements. Time for chemistry to increase in complexity. The more we learn about early chemical enrichment from Webb, the earlier that last ingredient, carbon-based chemistry, becomes available in the universe. Life on Earth took roughly 400 million years to appear after the planet formed. If planets around early stars formed as soon as heavy elements became available, and if the chemistry of life can develop in that same 400 million year window, then the first potentially habitable worlds in the universe could have appeared over 12 billion years ago. That's a timeline that exists in a universe currently 13.8 billion years old, meaning any civilization that arose on one of those early worlds and somehow survived would be 12 billion years old today. That number is so large, it becomes almost impossible to reason about. A civilization 12 billion years more advanced than ours would have had enough time to develop and run through technologies that we can't yet imagine existing, let alone describe. The concept is speculative. No one has confirmed that life arose in the early universe. The chemical and physical conditions on early planets may have been hostile in ways that delayed or prevented biology. The radiation environment in the early universe was more intense. The heavy element concentrations were lower than in modern planetary systems. Life might require conditions closer to what Earth had, but Webb's data has made the early appearance of habitable planets a scientific question, where it was previously an assumption that it couldn't happen. The window is open in a way it wasn't 3 years ago, and the implications of that open window stretch into territory that most astronomers are careful about discussing in professional settings. What it means for humanity's place in time is even harder to sit with, because if older civilizations could exist, and if some fraction of them survived long enough, the question of why we haven't heard from them gets heavier with every observation Webb makes. In 1950, physicist Enrico Fermi sat down to lunch with colleagues at Los Alamos and asked a question that has unsettled scientists ever since. If intelligent life is common in the universe, and if civilizations spread over time, then the Milky Way should be full of signals, probes, or visitors by now. The galaxy is old enough that even slow-moving expansion should have covered it many times over in billions of years. So where is everyone? This became the Fermi paradox. Decades of debate have produced dozens of proposed solutions, ranging from the idea that life is far rarer than we assume, to the idea that civilizations destroy themselves before spreading, to the idea that advanced civilizations go quiet in ways we can't detect. Webb's findings add a new dimension to the paradox. If rocky planets capable of supporting life existed as early as 12 billion years ago, then civilizations with a 12 billion year head start on humanity are at minimum theoretically possible. The question of where everyone is becomes not just interesting but urgent. The age gap matters enormously. Humanity has had technological civilization for about 10,000 years. We've had radio technology for about 150 years. In 150 years of broadcasting, our radio signals have traveled 150 light-years into space, reaching a tiny fraction of the Milky Way's 200 billion stars. A civilization with even a 1,000-year technological head start on us would have capabilities beyond our ability to meaningfully predict. A civilization 1 million years old would be as far beyond us as we are beyond bacteria. A 12 billion year old civilization is a concept that requires abandoning most assumptions about what technology, intelligence, or civilization even mean. Some researchers take a practical approach. If such civilizations exist and are as advanced as that timeline implies, they have either chosen not to communicate with us in ways we can detect, they have gone extinct, or the signatures of their existence are present in our data and we haven't recognized them as artificial. Webb is producing data across an enormous range of wavelengths and distances. One of its secondary scientific programs involves looking at the atmospheric chemistry of exoplanets, planets orbiting other stars, and searching for biosignatures, chemical imbalances in planetary atmospheres that biology tends to produce. Oxygen and methane coexisting in an atmosphere is a strong biosignature, since they react with each other quickly and require constant biological replenishment to both be present at once. Webb has already detected carbon dioxide and water vapor in the atmospheres of certain exoplanets. It hasn't found an unambiguous biosignature yet, but its sensitivity is improving and its target list is growing. The possibility of ancient civilizations isn't a scientific conclusion. It's a logical consequence of the timeline. Webb's discoveries are opening up. Whether life actually arose in the early universe, whether it survived, whether it left any trace we could ever detect, all of that remains unknown and may remain unknown for a very long time. What changed is the timescale on which these questions now legitimately operate. Webb moved them from pure speculation into territory adjacent to testable science. And all of it, the galaxies, the black holes, the planets, the potential civilizations, rests on a model of reality that Webb is actively stress testing. What happens if that model needs to be replaced? Science doesn't work the way movies portray it. In movies, a single discovery overturns everything. One experiment, one genius, one moment, and the old understanding collapses. In reality, scientific revolutions are slow, messy, and usually involve years of mounting pressure before a new framework emerges. The standard model of cosmology isn't going to be proven wrong tomorrow. It might not need to be replaced at all. But if the weight of Webb's findings and the unresolved tensions in the data do eventually force a revision, the scale of what changes depends entirely on how deep the revision goes. The least dramatic scenario is a patch, a small modification to one or two parameters, maybe an adjustment to how dark matter interacts in dense environments, or a tweak to inflation models to allow larger early density fluctuations. The core of the standard model stays intact, the history of the universe stays roughly the same, and the early galaxy problem gets explained as an edge case the original simulations didn't capture. Most scientists consider this the most likely outcome. A more significant revision would involve adding a new ingredient, something like early dark energy, a form of energy that existed in the very early universe and affected structure formation before leaving no other detectable trace. This wouldn't break the standard model, but it would expand it, the way adding dark energy to the model in the 1990s expanded it without destroying its previous successes. The most dramatic scenario is a paradigm shift, a replacement of the standard model with something fundamentally different. This would happen only if the data accumulates to the point where patches and additions can no longer hold the framework together, and a competing model outperforms it across a broad range of observations. Historically, paradigm shifts in physics have been preceded by exactly the kind of accumulating anomalies that cosmology is now facing. If a paradigm shift came, what might replace the standard model would depend on which current alternative best fits the full body of evidence. It could be a modified gravity theory, since some researchers argue the failures of dark matter predictions suggest gravity behaves differently at large scales than general relativity predicts. It could be a bouncing cosmology, where the Big Bang was a transition from a previous phase. It could be something no one has written down yet. What would stay the same? The fact that the universe is billions of years old, that it started in an extremely hot and dense state, that it expanded and cooled into the structure we observe today. The Big Bang framework, at the level of basic history, has too much evidence behind it to be overturned without extraordinary alternatives. What might change? The specific timeline of structure formation, the nature and properties of dark matter, the behavior of dark energy, the story of what happened in the universe's first moments. and the relationship between our observable universe and whatever, if anything, exists beyond its edge. For anyone listening, the practical takeaway isn't uncertainty. It's the opposite. Science is functioning exactly as it should. A new tool found something unexpected. The field is examining it rigorously. The answers will come through observation, not argument. And more observations are on the way. What comes next in this story is more powerful than anything that has come before it. Webb launched with a design lifetime of 10 years, fueled for its journey to Lagrange 2, and calibrated for the cold and the dark. The launch was so precise that it used less fuel than planned, and engineers calculated shortly after launch that Webb might operate for 20 years or more. That's double the original estimate, and it means the science is far from over. Webb has so far published results from a fraction of its planned observing time. Its schedule is packed with approved programs from scientists across dozens of countries, covering topics from nearby exoplanet atmospheres to the most distant objects the universe contains. Every month brings new data releases, new surprises, and new papers challenging previous assumptions. The telescope's most critical ongoing work involves building a complete census of the early universe. The early galaxy discoveries that shook the field came from relatively small survey patches. Webb is now expanding those surveys, covering more sky, probing deeper, and targeting specific regions where gravitational lensing allows it to see even fainter and more distant objects than it could otherwise detect. Each new survey adds statistical weight to the findings. The early galaxy problem becomes harder to dismiss when it shows up consistently across hundreds of independent detections in different parts of the sky. Webb is building that case in real time. On the ground and in space, a new generation of observatories is preparing to join the effort. The extremely large telescope, currently under construction in Chile, will be the biggest ground-based optical telescope ever built, with a mirror over 128 feet across. At that size, it will resolve structures on individual galaxies in the early universe that Webb can only detect as points of light. It could confirm or refute the mass and brightness measurements Webb has produced, and it will detect stellar populations in early galaxies with precision that current instruments can't approach. The Nancy Grace Roman Space Telescope, scheduled for launch in the next few years, will survey the sky in infrared at Webb's wavelengths, but across an area 100 times larger per image. Where Webb has looked at small patches in extreme depth, Roman will map enormous swaths of sky and find rare early galaxies in numbers that will transform the statistics from dozens to thousands. These telescopes won't just confirm Webb's findings. They'll push into new territory, looking for the signatures of population 3 stars in individual galaxy spectra, mapping the cosmic web at multiple stages of evolution, tracing the chemical enrichment of the universe from its earliest moments to today. The question that might never be answered sits at the edge of all of this. What happened before the Big Bang? Physics breaks down at that boundary. The equations that describe the universe stop working at the moment of maximum density and temperature. Whether something preceded the bang, whether our universe is one of many, whether the laws of physics themselves were different before the expansion began, those questions may be forever outside the reach of any instrument built in our universe, because the evidence, if any exists, would be buried under 13.8 billion years of subsequent history. Webb won't answer that question, neither will the telescopes that follow it, but it is asking every question that can be asked, one observation at a time, pressing as close to that boundary as physics allows. And the answers it's already finding are more extraordinary than anyone building it dared to promise. In December 2021, a rocket carried Webb into space on a journey that took about a month. The telescope unfolded slowly, mirror panel by mirror panel, sunshield layer by layer, a choreography of 344 mechanisms that had been tested thousands of times on the ground and then executed, without human intervention, 1 million miles from Earth. 6 months later, the first images arrived. Galaxies existed when the universe was 290 million years old. Black holes had already grown to 1 billion solar masses. Chemical elements that require multiple stellar generations to produce were already present in the gas of early galaxies. The cosmic web was already organized. Clusters were already forming. Reionization was already underway. The universe built itself faster, more efficiently, and on a larger scale than every model we constructed over 50 years of careful observation. And the gap between what we predicted and what Webb found isn't a small rounding error. In some measurements, it's a factor of 100. Here is what that means for you, right now, listening to this. Every atom in your body has a history that stretches back to the first stars. The iron in your blood was forged in a star that died billions of years ago, in an explosion so bright it briefly outshone an entire galaxy. The oxygen you're breathing was scattered by a supernova so old that the sun didn't exist when it happened. You are, in a completely literal and measurable sense, made of the universe's earliest work. The atoms in you are ancient. They were here long before you were. And that universe, it turns out, is stranger and older feeling than anyone calculated. It built structures we can't fully explain. It produced black holes that grew too fast, galaxies that formed too early, and chemical enrichment that happened in a window of time so short it breaks our best models. Scientists are not panicking. They're doing exactly what science does when something unexpected appears. They're looking harder, checking the measurements, running new simulations, proposing modifications, testing alternatives. The work is ongoing, the data is real, and the answers are coming, slowly, observation by observation. What Webb leaves us with is a feeling that's hard to name precisely. It's not fear. The universe being stranger than our models doesn't make it more dangerous. It's something closer to the feeling of standing at the edge of a map and realizing that the blank space beyond the edge is not empty. Something is out there. Something was out there before we existed to look. Something built structures we're only beginning to understand, on a timeline we're only beginning to measure, in ways we're only beginning to question. 13 billion years of light traveled to reach a golden mirror floating in the cold 1 million miles from Earth. The mirror caught it. Scientists read it. And the light said, quietly and precisely, that the story of the universe is larger than the story we told ourselves. That story is still being written. Webb is still looking. And whatever it finds next will be, by the pattern of everything it has found so far, something no one expected. Something that forces the question again. Something that pushes the boundary one step further back into the dark. The universe is not finished surprising us, and we are just getting started at reading what it has to say.